My objective for today is to discuss polar coordinate system. We understand how we can use this coordinate system to describe curvilinear motion, and then we will also apply this coordinate system to a special case of curvilinear motion, that is circular motion. So this would be the last topic in our this discussion of kinematics of particles. Before I start, I would like to acknowledge the textbook which I am using to prepare these lectures and training material. So these polar coordinates are also referred to as r theta coordinate system, and they will be another way of describing the plane curvilinear motion other than the xy coordinate system and nt coordinate system, which we have just discussed in last few sessions. So imagine that a particular particle is moving in a curved path, which is shown here by the dotted line. So this is the path of that particle. It is a curved path, and at a particular time instant the particle was at a point A, right? If we have a fixed origin in the same plane in which the motion is occurring, then we can have a radial distance denoted by the r symbol starting from that fixed origin to that point A, which is the location of that particle at a given time instant, right? So small r is representing the radial distance. We can define a coordinate r in the same direction, which is in the direction of r vector. Actually, the magnitude of that r vector will be this r, which is the radial distance, right? So the positive direction of r axis is defined as this one. So this is positive direction. So it is in the radial direction starting from origin to that point, right? And the perpendicular axis to that r axis is theta axis, right? So we can now define our curvilinear motion in terms of this r and theta axis, which are defined such that r's positive direction is in the direction of radial distance, right? And then perpendicular to that will be our theta axis. So the first thing we can notice about this r theta coordinate system is that it is also changing its direction at all time instants, just like the nt coordinate system, right? And unlike the xy coordinate systems. So just a quick review of xy coordinate system. So if we have an xy coordinate system and there is a curved motion described using that system, then we know that the x direction and y direction don't change their directions, they remain constant, but the position vector r actually change its direction all the time, and we can resolve that position vector r into its x component and y component. Similarly, in the nt coordinate system, if this is the t axis, this is n axis, then obviously t will be tangent to the path of the particle, and as the particle is moving, t will changing its direction, n will be changing its direction. Similarly, here also r and theta will also be defined such that they will be changing their directions all the time while the particle is moving, right? So at another time instant when the particle is somewhere here, you have a different r direction and a different theta direction, right? So the first thing you should notice is that if there is some rate of change of the unit vector in the r direction, that rate of change won't be zero, unlike the xy coordinate system. Similarly, if there is a rate of change of the unit vector in theta direction, that rate of change would also be not zero, right? Because they are changing their directions all the time. So let's define E sub r unit vector as a unit vector in the r direction and E sub theta as the unit vector in theta direction, right? So their magnitudes are 1, but at one time instant their direction is towards r and theta respectively, and at the next time instant their direction change to the new r and new theta direction respectively, right? So the magnitude of E sub r unit vector or E sub theta unit vector is equal to 1, right? But their direction is changing, right? The r vector, the position vector for a particular point, can be written as a product of its magnitude, which is radial distance r, times its direction, which is now described by the unit vector E sub r, right? So the direction of r is described by E sub r unit vector, right? So E sub r is describing the direction of r. Now after we define this coordinate system, the next step should be to see how we can write velocity vector and acceleration vector in this new coordinate system, right? So our next target should be to write v vector, right, in this new coordinate system and see what will be the r component of velocity, what will be the theta component of velocity. Similarly, the acceleration vector and its corresponding r and theta components, right? So that should be our next step. But before moving to that step, you should realize that all such motions in which the path is actually defined by controlling a position vector or a radial distance, in all such cases the use of r theta coordinates will be very useful or very convenient. For example, if I give you a path which looks like this, that from point A to B, the path is such that the radial distance remains constant throughout A to B, right? So for example, from some origin O to the distance A, and same distance from O to B also, and similarly if the distance remains same from O to some intermediate point also, it is now a constrained motion in which the path is defined such that we control this r, we keep it constant, and then we let the particle move in a curved path such that it remains at the same distance from a fixed origin. Now in this case, it will be very convenient to describe this kind of a motion from A to B in terms of r theta coordinates, because we exactly know what is the radial distance, and then radial distance is being rotated by an angle to produce that path, right? Similarly, if I continue and maybe the path continues like this, and from B to some point C there is another curved part of the path with a different radial distance, maybe now the center of that circle is here, but again this radius from some new O prime to B or from O prime to C remains constant again. So in that case also, maybe I call it r prime or r prime. In that case also, this kind of a motion will be conveniently described using r theta coordinates, right? Because it is having a definite value of radial distance, and that distance is being rotated by an angle at the center of that circle to actually produce the path of that motion. So in the design of machine assemblies, in the design of mechanical components, or in different other applications, you will be facing several constrained motions in which the motion is such that the path of the particle is being controlled by a radial distance. A particular radial distance is being rotated about a particular fixed origin to produce that path. In all such cases, you should know that polar coordinates are really handy. And also in some cases of unconstrained motion, but in those cases when the motion is observed by measurements of a radial distance and an angular position, right? So whenever you have a radial distance describing the location of a particle and the path is being described by the rotation of that radial distance, you should know that it is a case of polar coordinate system, right? Now let's move to the formulation for velocity vector and acceleration vector in this r theta axis, right? R theta coordinate system. Now if I do a quick exercise here, that obviously the velocity will be the first derivative of this r vector with respect to time. So if I do it here, for example, d by dt of r vector right? And this will become the velocity vector, right? Now I know that r vector can be written as the magnitude of r times the direction of r, which is described by the unit vector e sub r. So it will be the derivative of this product with respect to time, right? Now r alone can vary with respect to time, right? So at next time instant you have a new point of location, you have a different r, so r is varying with time, right? Circular case will become a special case when r becomes constant, right? But it is not necessary that r is not varying with time. Similarly, we have just discussed that E sub r, the derivative of E sub r won't be 0, right? So therefore, we can expand this differentiation, and that expansion will actually involve a term which will be the first derivative of this E sub r, right? So actually we need to first determine the first derivative of E sub r in order to write velocity in terms of its r and theta coordinates. Similarly, if I introduce that velocity term, for example, I carry out that that differentiation actually to determine velocity, and then I can differentiate it again to calculate acceleration. And that will also involve the derivative of E sub theta and E sub r, the unit vectors in theta and r directions respectively. So it means that the first thing we should do is to determine what is d by dt of E sub r unit vector and what is d by dt of E sub theta unit vector, because both of these quantities are appearing in my velocity expression and acceleration expression, right? So before actually writing velocity and acceleration in this coordinate system, let's determine this quantity and let's determine this other quantity, right? So let's look back again this figure, and at any particular time instant, if the unit vector in the r direction was represented by E sub r, at the next time instant the direction of E sub r for that point will be changing, right? So what I did here in this figure, that I draw the unit vector E sub r at a particular time, and after the time dt, like during time interval dt, the unit vectors change. So after the time dt, I draw a new unit vector E prime sub r, right? And it is describing the direction of r after time dt, right? So I can say this is the unit vector when the particle was at A, right? So at point A, and when it moved to some next point after the time dt, and that next point will have a slightly different direction of the E sub r, so it will be at some point, for example A prime, right? And the time difference between A and A prime, like the position at A and the position at A prime, the time difference between them is dt, right? dt. So actually what we can see here, that during that incremental time instant, that small time, the r actually rotated, because what is happening here, if you look at how the r is changing, it is being rotated by an angle theta, right? So whenever you go to a new point A prime, r slightly rotated, right? So then it rotated to new point and keep on rotating, and there will be increments in theta, right? So let's define an incremental like angle, a differential angle d theta, that is the angle with which this r direction rotated during the time dt, right? Obviously, if r rotated by an angle d theta, then in the same time dt, the corresponding perpendicular axis like the theta axis, they also rotated by the same angle d theta, right? So E sub theta is the perpendicular to E sub r, the theta axis direction when the particle was at point A, and E prime sub theta is the theta axis direction when the particle moved to a point A prime, right? So if the angle between E sub r and E sub r prime is d theta, then the angle between the corresponding theta axis will also be d theta, right? If I join the tip of E sub r with E sub r prime, this will be a vector describing the change in E sub r, right? So this change in E sub r is denoted by a vector called dE sub r, right? Similarly, if I join the tip of E theta with E theta prime, I get a new vector which is the change in E theta during time dt, and I denote it by dE theta with a cap on top. So it is a vector quantity which is the change in E sub theta. If I divide this vector by dt, this will give me the first derivative of E theta with respect to time. So this is what we want to determine. We want to determine time derivatives of E sub r and E sub theta, so that we can write velocity and acceleration in terms of polar coordinates, in terms of their corresponding r and theta components. One thing about the directions of r and theta axis, you can see here that the change in E sub r, dE sub r, is actually in the theta direction, positive theta direction. So if you actually see the direction of this particular change, it will be actually perpendicular to the original r, and that is the positive theta direction, just like we saw in the n-t coordinate systems that the change in t unit vector was actually in the direction of n unit vector. So same will be the case here, that the direction of this dE sub r, the change in the r unit vector, will be in the direction of theta. However, the change in the theta unit vector will be in the direction of minus r. Minus r means that you are going towards origin, right? So the direction of positive r is defined as when you have a particle here and you just extend the position vector from that point away from origin, right? So actually this is minus r direction, right? So you just look here that the change in the E sub theta, which is denoted by this vector dE sub theta, is in the minus r direction, right? R direction is this direction, this is r, this is also r, right? But the change is in the minus r direction. So now let's take this information and write the first derivative of E sub r and E sub theta. In order to write the first derivative of E sub r first, we need to determine the magnitude of this change in the unit vector, right? So change in the E sub r vector, let's see what is its magnitude. So I define magnitude with these two lines. So actually it will become this distance, right? This distance. Now this distance is simply the arc which the E sub r is making while rotating by an angle d theta, right? So we can simply apply that case, like if there is some distance r which is being rotated by an angle theta, we can determine this length L, that will be simply equal to r times theta, right? So it means that we can simply determine the magnitude of this E sub r vector, which is 1, and rotate it with an angle d theta to get this distance, right? And this distance is actually the magnitude of dE sub r. So this is what I wrote here, that length of the arc, that will be the magnitude of E sub r vector times the angle which it rotated. So it is simply L is equal to r theta, and the magnitude of E sub r is 1, d theta is same d theta, so we can say that the length of that change in the E sub r vector was equal to d theta. So if I go back, I can say that this length is equal to d theta, right? So now I can simply write the dE sub r vector as a product of its magnitude and its direction. We have just seen that the direction of this dE sub r is in the positive theta direction, so it will be multiplied by the E sub theta and the magnitude will be what we have determined earlier. So I can simply call this quantity dE sub r as E sub theta times d theta, where d theta is the magnitude and E sub theta is the direction of that vector. And finally I can divide this dE sub r with d theta, right? So I can just take this d theta as a denominator here or divide with d theta on both sides. I will get this expression at the bottom, right? Same exercise I can repeat for E theta also. So this is the vector describing the change in the unit vector E theta, right? So let's see what is its magnitude and what is its direction. The direction we have already seen, it is denoted by the minus r direction. So it should be actually multiplied by the minus E sub r unit vector. But let's see what is the magnitude. You can repeat that exercise and you can see here that the magnitude of this vector will be simply the magnitude of E theta being rotated by an angle d theta. So E theta's magnitude multiplied by the angle of rotation will be the length of this vector, right? So this length actually should be E sub theta's magnitude multiplied by the angle which is d theta, right? And if the magnitude of E sub theta is 1, it is a unit vector, so the length will simply become d theta, same as the case of E sub r. So the length is equal to d theta. However, the direction is in the minus r direction, so therefore we have simply repeated the same thing. The magnitude of dE sub theta is the length of that arc which E sub theta made by rotating an angle d theta. So we just multiplied by the magnitude of E sub theta by the angle which it rotates. This give us 1 times d theta and this will simply become d theta, right? However, the direction of the change in the E theta vector is given by minus E sub r now, because the change in E theta is in the minus r direction. So therefore we can write this dE theta vector as a product of its magnitude and its direction. So magnitude is simply d theta and direction is given by minus E sub r. So we get this expression, or I can rearrange it in this form also. So I just get what is dE sub r, right? Now I am in a position to calculate the first derivative of E sub r with respect to time. I can simply write dE sub r is equal to d theta times E theta, and this expression I can simply write it as dE sub theta unit vector change in the E theta is equal to minus E sub r times d theta, right? And I can divide by dt on both sides, here also and here also, right? So I divided by dt on both sides for both expressions. This actually give me now the first derivative of that unit vector with respect to time. So I can denote this equation now as E sub r unit vector and a dot on top representing its first derivative with respect to time is equal to, this will become theta dot, the first derivative of theta with respect to time. So let me just denote it with theta dot on top times E sub theta, right? And on the right hand side it will become E sub theta unit vector with a dot on top, which means the first derivative of E theta with respect to time is equal to, this quantity will become again theta dot, right? So let me write it as theta dot times E sub r unit vector with a minus sign in the start, right? So it will be minus theta dot E sub r, right? I repeated essentially the same exercise which I did for the n-t coordinate system, right? But if you remember, there we only required the first derivative of the unit vector in t direction only, right? But here we have actually requiring the first derivatives of both unit vectors, and that's how we actually determine them, right? So now we are in a position to write velocity and acceleration vectors in terms of their r and theta coordinates, and then if any of the first derivative is appearing in that formulation, we can replace them with these equations at the bottom left and bottom right, right? So this is the overall summary, that my first derivative of E sub r is in the direction of E sub theta, and it will be having a magnitude equal to theta dot. The first derivative of E sub theta is in the direction of minus E sub r, and it will also be having the same amplitude, which is theta dot, right? So if you remember, we have determined in the n-t coordinate system, we have determined the first derivative of E sub t there in that discussion, and that was actually same as this one, but obviously the direction was different, right? So it is analogous to the n-t coordinate system, with a difference that there we only required this quantity, but here we will be requiring the first derivatives of both unit vectors, right? So with this information, now let's start writing the velocity and acceleration in polar coordinates. I will start with velocity first. We know that the position vector is simply equal to the radial distance multiplied by the E sub r. The direction of position vector is defined by E sub r unit vector. I can take its first derivative, right? So V vector will become first derivative of the r vector. Now r vector is again comprised of a product of two quantities, so I can just evaluate that differentiation, the derivative of first quantity times the second quantity plus the derivative of second quantity times the first quantity. This in the dot notation will give me as V is equal to the r vector dot, which will become actually, this quantity will become r dot, right? First derivative of r with respect to time. Similarly, this quantity will become the first derivative of unit vector E sub r with respect to time. So I denote it with E sub r with a dot on top times r, right? This r. So now you can see here that we now need that equation which we derived the first derivative of E sub r, and that was actually from last slide. It was equal to theta dot times the E sub theta, right? So we can put this equation here in this place to complete our formulation for velocity, and the first term will remain same, r dot times E sub r. However, the second term will become r times theta dot times E sub theta, right? So this product is actually equal to this first derivative of E sub r. So now we have written velocity as a sum of two vectors. One vector is having a direction E sub r, other is having a direction E sub theta, right? So now it is a complete formulation of velocity vector as a sum of two components. We can call this quantity as the r component of velocity, and we can call this quantity as the theta component of velocity, right? So let's denote them as V sub r. So this become V sub r equal to r dot. Let's denote this as V sub theta, r theta dot, right? So at any time instant, we can also determine the magnitude of the total velocity using square root of Vr square plus V theta square, right? So we have resolved velocity into its r component and theta component. These two are the scalar relationships which we will be using to determine the magnitudes of r and theta component respectively, and the top equation we will be using to actually write the complete velocity vector at a given time instant. We can also write it as V sub r times E sub r unit vector plus V sub theta times E sub theta unit vector, right? So this will be our complete velocity vector at any given time instant, right? So we need r at a particular time, r dot at a particular time, and theta dot at a particular time to actually describe the complete velocity vector in terms of its r and theta components, right? So obviously the velocity vector, depending upon the algebraic signs of these the r and theta components of velocity can be positive, can be negative, it can be tangent in this direction, it can be tangent in this direction, right? So depending upon the algebraic signs of r dot and r theta dot, right? Now let's repeat the acceleration process for writing acceleration in this coordinate system. What should we do? Whatever velocity vector we have determined, let's take its one more derivative with respect to time, and that will give us a complex equation, a relatively complex equation for acceleration. So let me just write it here. The next step should be to write acceleration vector in this coordinate system. That should be d by dt of the v vector, right? And v vector we have just determined, it is a sum of two terms, and first term is actually r dot e sub r plus r theta dot times e sub theta unit vector, right? So the derivative will go to first term separately and then second term separately, right? Now each of these terms r dot, theta dot and both unit vectors, they are all functions of time, right? So no quantity out of them can simply come out from differentiation. So we have to apply the product rule to this product separately for differentiation, and the product rule for this differentiation separately. So let's evaluate that long differentiation now and see what will be the a vector. One thing is clear right from start, that we will be needing the first derivative of e sub r and first derivative of e sub theta to complete our acceleration formulation, right? So we will be actually using the same two equations, this one and this one, in our acceleration formulation. So let's evaluate that differentiation. Before that, this actually gives you the overall summary, right? The r component of velocity is this thing. It is the rate at which the vector r stretches, r dot, right? And theta component of velocity is due to the rotation of r vector. So actually it is a function of theta dot. It is a function of how fast or how slow theta is varying, the rate of change of theta with respect to time, right? One conclusion which we can draw from this expression about circular motion, that if r becomes constant, then obviously this r dot will become 0, right? In that case, velocity will only be having the theta direction, right, which will coincide with the tangent direction actually in circular motion case. So we can see that at the end of this discussion also, but just keep in mind that for circular motion case, when r becomes constant, r dot will be simply 0. So now let's go to our acceleration discussion and let's write the first derivative of velocity vector with respect to time. This is our acceleration, which can also be denoted as v vector dot, right? And this will actually become this whole v vector, right? And then we can evaluate that differentiation. It will go separately to first term, it will yield me this thing, and it will separately go to the second term. This will actually yield me this long expression, right? So let's do that exercise quickly. So this thing I can write it as d by dt of r dot e sub r unit vector plus the differentiation will go to the second term, it will become d by dt of r times theta dot e sub theta unit vector, right? So this thing, this first differentiation will expand into, when we apply the product rule, it will simply become r double dot, the first derivative of first quantity. First quantity was already r dot, so it will become r double dot times the second quantity as it is, plus the first derivative of the second quantity, which will actually become the derivative of this E sub r. So I put a dot on top, multiplied by the first quantity as it is, so that will be r dot, right? So it should actually, first derivative is resolved into two terms here, r double dot times E sub r plus r dot times the first derivative of E sub r, which is denoted as E sub r dot on top. Similarly, this product, actually it is a product of three terms, so we can first consider these two terms as together and apply the product rule, and then we can also apply the differentiation of this product and expand it further. So I can write it as, let's use r theta dot as the combined quantity in the first case. So it will become the r dot theta double dot when we have the, let me just expand it further. So let me write it as, only this term will become d by dt of r theta dot multiplied by the second quantity as it is, right? So this E theta is kind of second quantity in this case, plus the d by dt of second quantity E sub theta times the first quantity as it is, which is r theta dot, right? So this actually differentiation will in first step resolve into two terms, but we know that this is now again a product, so this quantity which I am encircling now will again result into two more terms, right? So this final thing will become, if I expand this box, it will become r dot theta dot plus theta double dot times r, right? So the derivative of first times the second quantity plus the derivative of second, which will become theta double dot times the first quantity, right? And this whole thing is being multiplied by E sub theta, right? Plus this thing, which will actually become E sub theta dot on top times r times theta dot, right? You can multiply this E sub theta and you will result in three terms actually, right? And then finally those three terms will be these three terms, right? These three terms you can confirm from here. You should have r dot theta dot E theta, right? So this is r dot theta dot E theta. You should have r theta double dot E theta, and this is r theta double dot E theta, and finally you should have r theta dot E theta dot, which is this first term r theta dot E theta dot, right? And in addition to that, first two terms from the first part of differentiation will be there, right? So everyone is clear how I came up with that long expression, right? Simply the application of product rule in two steps. Now you can see that acceleration vector is this long term, and it has a term which is being multiplied by E sub r, which is being multiplied by E sub r dot, similarly theta E sub theta dot, and similarly E sub theta, this one and this one, right? So let's put those two equations which we just derived, this one and this one, to write all terms whether in a product of E theta or E r, right? So I introduce this equation E sub r, I introduce it here, right? Similarly, I introduce E sub theta here in the first term, right? So all my long expression for acceleration is now not a function of the derivatives of unit vector, but it is written only in terms of unit vectors. So I can take all those quantities which were being multiplied by E sub r, I can take E sub r common, and I can get this whole thing being multiplied by E sub r. Similarly, I can take E sub theta common from all those quantities which were being multiplied by E sub theta, and I will get this whole quantity times E sub theta, right? Now if you look at this box, I have written acceleration as a sum of two vectors. One is in the direction of E sub r, one is in the direction of E sub theta, and both of those components have this magnitude for E sub r component and this magnitude for E sub theta component or the theta direction component. So we can call this whole quantity as A sub r, the magnitude of the r component of acceleration, and we can call this whole quantity as A sub theta, which is the magnitude of theta component of acceleration, right? So now you can see that unlike velocity, we have relatively complex equations for A sub r, A sub theta, and they require double derivatives like second derivative of r and second derivative of theta also, right? So r double dot is required to calculate A sub r, which will be actually d2r by dt square. Similarly, theta double dot is also appearing here, so we need actually the second rate of change of theta, so d2 theta by dt square, right? So one more information which you must think here right at this stage, that you need to have r and theta as a function of time if you want to determine their first and second derivatives, right? So not only you need r dot and theta dot, you also need their second derivatives also to calculate the r and theta components of acceleration, right? And at any given time instant, if you can determine these four quantities, actually five quantities, r, r dot, r double dot, theta dot and theta double dot. These five quantities you need in both equations to calculate both components of acceleration. If you can determine it at a given time instant, then you can calculate the total acceleration magnitude as a square root of A sub r square plus A sub theta square, right? And again, the algebraic sign of A sub r and A sub theta will tell you whether that component is in the positive r direction or negative r direction, right? Or positive theta direction or negative theta direction, right? So this is the summary now for acceleration. Acceleration, we have written it as a sum of this vector plus this vector. This vector whole thing is the r component of acceleration and its magnitude is this quantity and its direction is the E sub r. And the second vector was the theta component of acceleration with a magnitude equal to this quantity, which I am encircling now. We can call them as A sub r, A sub theta. So graphically, if this is the path of a particle shown by the dotted line, right, and if this is the velocity vector, acceleration vector A, right, it will be neither tangent or normal to the path, it will have the direction which is in the direction of the change of velocity. At any given time instant, we can resolve it into two components, one along r direction, so this is the positive r direction, and perpendicular to that is the positive theta direction, right? We can resolve that acceleration vector into its r component, which will have this magnitude, and its theta component, which will have this magnitude, right? So now you will be repeatedly applying these scalar expressions to resolve any acceleration vector into its r and theta components, right? For keeping the discussion simple, I will skip the geometric interpretation and directly go to one or two solved examples towards the end of this discussion. So although I included it in my notes here, but these couple of slides I will not be explaining. What I essentially do in these slides, just like in anti-coordinate system, I came up with the same expression or same two components of acceleration geometrically. This is what I am doing here for r and theta coordinate system also, that I am actually writing the v vector at a particular time and the v vector at the next time instant or after time dt. Then I am resolving the change in velocity vector into their r and t, actually r and theta components, to calculate what is the r and theta components of acceleration, right? So actually the whole summary of last 2 or 3 slides is that you can come up with the same a sub r component or a sub theta component geometrically also, right? So it will answer the questions like why a sub r component need to be this whole quantity, right? So it is like making a geometric sense of what r double dot is or what this quantity is, right? Similarly, making a geometric sense of both of the terms in the a sub theta. Before moving to the solved examples, let's apply this interpretation of velocity and acceleration in polar coordinate system to a special case of curvilinear motion, which is circular motion, right? So what will change in circular motion? First of all, r becomes constant, right? So wherever r dot is appearing, it will become 0, right? We can now describe the circular motion in polar coordinates. So these are the r and theta components of velocity which we have just derived. These are the r and theta components of acceleration. We have just seen that. So let's apply them to the case of circular motion. So let's say that a particle is moving in circle with constant radius, and at any given time instant its location is this point P. The r axis will be, the positive r axis or r direction will be this dotted line, which will be joining actually O to P, and perpendicular to that will be your theta direction, right? Now theta direction will actually coincide with your tangent direction in this case, right? So actually theta is coinciding with the tangent of the path, which is the orange color circle here, right? So the velocity v at any time instant when the particle was at P point will be tangent to that path or actually in the theta direction, right? This can be confirmed mathematically also because we know that the r component of velocity in the polar coordinate is r dot, which actually becomes 0, right? So it means that velocity in a circular motion case will always be in the theta direction, or it will only have the theta component. It won't have any r component, right? So v sub r will always be 0 in circular motion case, while there will be some v theta, right? And that will be equal to r times theta dot. So in short, in circular motion case, theta direction and tangent direction coincide with each other, and velocity don't have any r component. However, acceleration will still have both components, but we can introduce, for example, r double dot will become 0 for circular motion case. R dot is 0, so r double dot is also 0. Similarly, this quantity will also become 0 because it is involving r dot, right? So we will simply be having the expressions a sub r equal to minus r theta dot square, and a sub theta is equal to r theta double dot. So simple equations for components of acceleration in polar coordinate system, right? Now let's compare them with the expressions we derived for the nt coordinate system, right? If you remember the n component of acceleration, right, it was equal to r theta dot square in the nt coordinate system. Similarly, the t component of acceleration was equal to r theta double dot, right? If you compare this pair of equations with this pair here, you can simply confirm. First thing you can see that a theta is same as a sub t, right? So it also confirms that theta direction in circular motion case coincides with the tangent direction, right? So either you call it the tangent component of acceleration or theta component of acceleration, same quantity, right? So theta and t direction coincide in case of circular motion, and similarly if you compare a sub n with a sub r here, you can see that there is a minus here but there is no minus here, right? So plus r in the circular motion case in polar coordinates is actually in the minus n direction in case of n and t coordinate system. So actually A sub r actually is in this direction, which is minus r, right? So minus r coincides with the normal direction, right? So A sub r is equal to minus n. If you describe the same circular motion in terms of nt coordinate system, you will see that this direction will be actually plus n direction, right? But in our polar coordinate system, this direction is actually minus t direction. So therefore, you are having A sub r equal to minus A sub n. So while theta and t direction coincide exactly, r and n have opposite directions, right? So plus r will have a minus n direction. So obviously plus n is towards the center of curvature, minus n will be away from the center of curvature, that is plus r, right? So r and n will always be having opposite directions, and therefore you have a minus here with the same magnitude but without minus here. So an is equal to, ar is equal to minus an, or an is equal to minus ar, right? This is the case when circular motion is centered at the origin of polar coordinates, when you have the origin same as the center of that circle also, right? One more insight which you can have while applying polar coordinates to circular motion. If you have described the circular motion in xy coordinate system, you know the corresponding equation for x and y. X is equal to r cos theta, y is equal to r sin theta. If you plot x and y using these two equations for any given r, you will see that it is describing a circular motion, right? At any given theta and r, you can calculate a pair of x and y, and if you plot enough pairs of x and y, you will get a circle, right? Now in xy coordinate system, we also have the x component and y component of acceleration, which is simply the x double dot and y double dot, right? We can introduce this equation, take its two derivatives, similarly introduce this equation here, take two derivative, and they will be our x and y components of acceleration in x and y coordinates, right? One thought experiment you can do, or you can do it graphically also, that resolve each of these a sub x and a sub y into their corresponding r and theta components. So for example, draw x and y for a particular point, and also draw r and theta components, for example r and theta, right? So if for example this is your origin, so obviously r will be this direction, but x will be this, y will be this, right? So you can resolve each of this a sub x and a sub y into a sum of its r component and t component. Actually the total acceleration along r axis will become a sub r, and total acceleration along theta axis will become a sub theta, and you will be getting same two expressions which you have just seen in the earlier slides, right? One more thing is that in polar coordinate system, you are seeing that the term theta dot and theta double dot are appearing in both of the acceleration components. Theta dot is angular velocity, theta double dot is angular acceleration, and their units are radian per second and radian per second square respectively. We have seen in the last session also how we can convert degrees to radians and radian to degrees, right?